Welcome. Have you ever wondered how your phone, your laptop, or even the smart TV you're watching actually process information? It seems like magic, but it's based on one single concept: binary numbers. We use base, 10, decimal, because we have 10 fingers, right? But computers don't count in 10, they count in 2. Today, we are going deep into the fundamental language of computing, binary. By the end of this session, you won't just know what binary is. You'll understand why every single piece of digital information, every photo, and every text message is ultimately just a pattern of zeros and ones. Are you ready to peek under the hood of the digital world? Before we dive into the math, let's talk physics. Computers are physical machines, and they run on electricity. Electricity is inherently simple. A circuit is either complete, allowing current to flow, or it is broken. This on or off state is the perfect analogy for binary. Instead of complex switches, we literally have voltage thresholds. If the voltage is above a certain point, it's a 1. If it's 0, it's a 0. This limitation, only 2 states, is what makes binary so powerful and efficient for machine use. It simplifies the entire world of data into nothing more than electrical signals. What do you think happens if the signal gets too weak, maybe picking up noise? In our familiar decimal system, we use powers of 10, the ones place, 10 to the power of 0, the tens place, 10 to the power of 1, the hundreds place, 10 squared, and so on. Binary does the exact same thing, but instead of powers of 10, we use powers of 2. This is the secret sauce of binary math. If you look at the place values in binary, they follow a geometric progression: 2, which is 1, 2 superscript 1, which is 2, 2 superscript 2, which is 4, 2 superscript 3, which is 8, and so on. Instead of needing 10 unique symbols, we only need 2, 0, and 1. This concept drastically limits the number of components needed while allowing for exponential growth and capacity. This is much more efficient than any base 10 system for electrical circuits. When we talk about binary, we start with the bit, which is short for binary digit. This is the absolute smallest unit of data, and it can only be 0 or 1. Because of this limitation, we group bits together into units called bytes. A byte is standardized to be 8 bits long. Think of a byte as a container that can hold 256 unique values, from 0 to 255. This 8-bit structure is critical because it allows us to encode a single character, like the letter A, or a single color value, allowing computers to manage massive amounts of data efficiently. If you had to store a whole word, you would need multiple bytes. Understanding the byte is key to understanding file sizes. Let's use the classic light switch analogy. Imagine you have 3 light switches. Each switch can be either on, 1, or OFF, 0. If you have one switch, you have 2 options, 0 or 1. With 2 switches, you have 4 combinations, 0, 0, 0, 1, 10, 11. Now, if you add a third switch, you suddenly jump to 8 possible combinations. This demonstrates the exponential growth of binary. It's not about adding options. It's about combining existing 2-state options. If you had 32 switches, you could represent over 4 billion unique numbers. This shows why binary is the perfect tool for counting and representing complex data within limited electrical resources. Converting from binary, base 2, to decimal, base 10, is actually much simpler than it seems. You don't need complex formulas, you just need to know the place weights. You look at the binary string, starting from the rightmost digit, and assign the weights: 2 to the power of 0, 2 to the power of 1, 2 squared, and so on. If a bit is a 1, you keep that weight. If it's a 0, you ignore it. Our goal is simply to sum up all the weights corresponding to the ones. This process is straightforward addition. Think of it like picking a combination of weights from the list: 128, 64, 32, 16, 8, 4, 2, 1. We just add the ones that are on. Let's work through a small example together. We have the binary number 101. First, we assign our weights starting from the right. The rightmost 1 is in the 2, 1 position. The middle 0 is in the 2 superscript 1, 2 position. The leftmost 1 is in the 2 superscript 2, 4 position. Now, we only sum the weights where we have a 1. So, we take the 4 from the first position, plus the 1 from the last position. For plus 1 equals 5. That's it. The binary number 101 is simply the decimal number 5. This works regardless of how long the number is, as long as we correctly identify the corresponding $2 carat in dollar weight for each position. Let's tackle a slightly longer example. 101101111. This number is 8 bits long, so our weights go all the way up to $2 carat $7, which is 128. We follow the same process. We look for every 1 and add its corresponding weight. We have 128, and then 32, and 16, then 4, 2, and 1. If we add those up, $128 plus 32 equals $160. $160 plus 16 equals $176. $176 plus 4 equals $180. $180 plus 2 equals $182. Finally, $182 plus 1 equals $183. This systematic approach ensures we never miss a weight, no matter how many bits the number has. This demonstrates the sheer scale of information we can encode. Now, let's reverse the process, going from decimal to binary. The easiest method is the repeated division by 2. What we do is take our decimal number, divide it by 2, and record the remainder, which will always be 0 or 1. Then, we take the quotient from that division and repeat the process. We keep doing this until the quotient finally becomes 0. The binary number is formed by reading the remainders in reverse order, from the last remainder up to the first. It's a simple, reliable loop that allows us to translate our familiar base, 10 thoughts, into the machine's native language. Let's convert 45. We start with 45 divided by 2. The remainder is 1. Then we take 22, remainder 0. Then 11, remainder 1. We continue this pattern until we get to 1, remainder 0, and finally 0, remainder 1. Now, we must read the remainders from the bottom up. 1, 0, 1, 1, 0, 1. That gives us 101101. To check our work, if we convert 101,101 back using the weights, 32 plus 8 plus 4 plus 1, we get 45. This confirms the process works perfectly, moving us from the human concept of 45 to the computer's binary representation. Binary addition is surprisingly simple, but you must remember the carry mechanism. It works exactly like decimal addition, but the base is 2. When we add $1 plus $1, the result is 2, but since we are in base, 2 is written as 10. So, we write down a 0 and carry a 1 to the next column. In our example, 011 plus 001, we add the right columns. $1 plus 1 equals $10. We write 0, carry 1. Next column, $1 plus 0 plus 1, ext carry, equals $10. Write 0, carry 1. Final column, $0 plus 0 plus 1, ext carry, equals $1. The result is 100. This shows that binary arithmetic is purely positional and follows simple rules, making it ideal for hardware implementation. It is vital to keep the terminology straight. We have the bit, the byte, and then larger units. Remember, 1 byte is always 8 bits. This container of 8 bits gives us 256 possible combinations. If we only had 7 bits, we could only store 128 values. This limitation is why file sizes are measured in bytes and multiples thereof. When you talk about storage, whether it's a single character or a massive video file, you are always dealing with these fundamental byte boundaries. Understanding this helps us grasp the physical constraints of digital memory. If we had a storage device that only used 4 bits per character, what limitations might that place on our ability to store modern text? Let's clear up a common misunderstanding. Many people assume that binary is just a counting system using 0, 1, 2, 3, up to 9. But that is incorrect. Binary is a positional system that only uses the digits 0 and 1. The digits 2 through 9 simply do not exist in the base 2 system. If you try to put a 2 in a binary number, the computer doesn't know what to do with it. The entire system is built on the absolute simplicity of the binary choice, on or off. Understanding this constraint is foundational to understanding how digital logic circuits operate. Another common mistake is confusing the number 10 in binary with the number 10 in decimal. If you read the sequence 10 as a number, you must remember that you are reading it in base 2. In our system, the rightmost 0 is $2 $1, and the leftmost 1 is $2 $1 2. Therefore, 102 actually represents the decimal number 2. The value of a sequence of digits is determined by the base you are using. This concept of the underlying base is crucial. It reminds us that binary isn't just a different way of writing numbers. It's a fundamentally different mathematical system. How does the computer store the letter A? It doesn't store the shape of A, it stores a number. And that number is stored in binary. The American Standard Code for Information Interchange, or ASCII, is one of the original methods that assigned a unique number to every letter, symbol, and punctuation mark. For example, the capital letter A is assigned the decimal value 65, which translates to the binary sequence 01000001. This principle applies to everything. When you type an email, the computer isn't seeing letters. It's seeing a massive stream of these numerical codes, 1 byte for every character. This realization is the key to understanding all digital data. Binary isn't just for text. It powers the entire visual world. Think about a digital color. To describe a single point of color, a pixel, you need to specify its intensity of red, green, and blue. This is the RGB model. Each color channel requires 8 bits, 1 byte, to specify its intensity, giving us over 16 million possible colors. Similarly, your IP address, which tells the world where you are online, is structured as 4 separate groups of 8 bits. From the color of a sunset to the location of a server, the underlying language remains the same. The elegant simplicity of the 0 and the 1. Everything is quantified